Okay. I'll come to this pure torsion case. So you have completed the pure bending and pure axial loading. Now you have come to the pure torsion case. So here once again, if I take a section here now, for the axial load 0, bend moment is 0, shear force 0, only twist moment is what, a plus T. So here you are getting this figure representing a prismatic member under pure torsion, a prismatic member under pure torsion. On the cross section, you are getting only torsional shear stress. Which stress 0? No, axial stress 0, bending stress 0, and direct shear stress 0. Only torsion. But what is the tensile stress in the shaft? What you have studied under pure torsion? Pure shear state of stress. This is a pure shear state of stress. On the cross section, you are getting tau xy. Tau xy associated with the tau yx. This leads to what now? Pure axial loading, you are getting a uniaxial state of stress. Pure torsion, you have studied. On the cross section, you are getting only torsional shear stress, tau xy, pure shear state of stress. Then you have studied what the maximum tensile, maximum compressive, and maximum shear stress all are equal. They are equal to 16 T by pi d cube. This also you have studied now. So here on the cross section, axial stress, bending stress, means on the cross section there is no normal stress. On the cross section there is no normal stress. So whenever you want to get a normal stress in the cross section, there should be a either axial load or bendment is required. Since there is no axial load, no bendment, no normal stress, only torsional shear stress is there now. For this one, what the equation is studied now. on the cross section. But in the member or in the shaft means what you have studied now? In the member. On the cross section there is no normal stress, only shear stress is there. In the member means what you have studied now? Maximum tensile stress, maximum compressive stress, maximum shear stress means what? In plane and absolute and tau star, there are equal to tau T max. What is the reason? Because of pure shear state of stress. That is sigma x plus sigma y 0. So for this case only torsion equation is valid now. Torsion equation is what valid now. So the torsion equation is valid what now? When a prismatic member under pure torsion. So once again what now? How we got this T by ZP from this only? For the J polar moment of here, which is the polar moment of inertia means IZZ. So by equating these two, what the tau max now? TR by J. Just like bending case now. So tau T max equal to TR by J. And what the other equation? Tau T max equal to GR theta by L. A is equal to B is equal to C. So how many ways you can find out the tau T max? You can equate A and B and B and C. So from these two now. When you are studying the polar section modulus definition, you have studied now J by R. Similarly, by equating these two, second and third, what the other equation you are going to get it now? Similarly, by equating the 1 and 3, what the theta angle of twist? Theta the angle of twist. What you have studied now, when you apply a twisting couple, the cross section is rotated about polar axis. So the rotation of a cross section about polar axis is called as what? Angle of twist. What the twisting and bending you have studied now? Twisting is the rotation of a cross section about polar axis. By how much angle is rotated about the polar axis is nothing but the theta. Theta the angle of twist. Now if I equate these two now 1 and 3, if we equate this 1 and 3, if we equate 1 and 3, what the theta? This represents this represents represents the angle by which the cross section rotates about polar axis. That is the angle of twist. J the polar moment of inertia. So whenever you want to use the equation, what the condition now? Whenever you want to use the equation, what the condition now? First of all, it should be a prismatic, pure torsion and same material. Is a prismatic, pure torsion and same material. संजीव गुप्ता क्या करना जी? चैप्टर नंबर 7 क्वेश्चन नंबर 23 27 क्या करना उसको? आप लाइव चैट में ऐसा लिखे तो क्या करना उसको? CH7 Q23 and Q27 means what I have to do it now? What do you want to convey it there now? Chapter number 7, nothing. You're informing that to your friends or what now? Technical team or what now? Simply your mention what now? Chapter number 7, question number 23, 27 by Mr. Sanjeev Gupta. You are informing that one to what now? Your office boy or technical person or your friends or teacher, what you have to do it now? Try to convey what you want to convey it now. Simply writing chapter number 27, Q23, question 23, question 27. What I have to do it now? To whom you are informing now? You are sending that information to what now? The technical person or what? Draw these lines now. Radial lines. These are the radial lines. This is the initial position before applying the twisting couple. But after applying the twisting couple, what happens? The cross section is going to be rotated about polar axis. When this cross section, this is which axis now? Is the polar axis. So this cross section will rotate about polar axis. When the cross section is rotated about polar axis, so this angle you are calling as a theta. Theta. A is representing what? The CA. CA is the initial position. CA dash is the final position. So this angle is the angle of twist. So that theta is representing what? By how much angle the cross section is rotated. That will I written now. Represent the angle by which the cross section rotates about polar axis. When A is twisted by the angle of theta, all the points are twisted by the same angle. When A is twisted by the angle of theta, all the points are twisted by the same angle. Is a cross section. This is about a twisting couple. The ETSL, ETSL, ETSL. Now this will form a twisting couple. This couple is parallel to the cross section. Now this couple is about which axis? Now polar axis. This couple will be about polar axis. So the cross section will rotate what about this axis now? Is it a clockwise, anti-clockwise, and anti-clockwise? So this is a rotation of a cross section about polar axis. Is it anti-clockwise, clockwise, and anti-clockwise? Now I've taken the four radial lines CA, CB, CE, CD. Now this is the initial position when the cross section is going to be twisted in the anti-clockwise direction, because this is the anti-clockwise direction now. Somewhere A is going to be twisted here. This is what a theta. Like this, what all the radial lines are twisted by the same angle. All the represent. Like this what now every point on the cross section is rotated by how much angle now theta. So this is called the angle of twist of a cross section at the free end, angle of twist of a cross section at the free end. So what this black color line initial position, red color lines are the final position. This is what the C. So like this what how many points are infinite points? All the points are twisted by the same angle. This is called the angle of twist. Because this is anti-clockwise, clockwise, and anti-clockwise. Either ETSL, ETSL, horizontal ETSL. This is what the polar axis. So it is rotated in what anti-clockwise direction. About which axis? No, polar axis. So how much angle is rotated? Theta. But how to get that theta value? No, theta is going to be always what you have studied. No, strain, deformation, they're all obtained experimentally. But theoretically, how to find out? By using the equation. Theoretically, we can find out the what now? What the aim of the strengthometry is studied now. Derive the expression for stress, strain, deformation under different loading. So this theta is going to be obtained experimentally. But theoretically, how to get it now? By using the equation TL by GJ. So this is about the torsion chapter now. So I'm going to write, already explained just before the break. Now I'm writing all the terminology here. Bending equation. Here is about the bendiment on the cross section of beam. How to get this now? Algebraic sum of the couples and moments either on the left side or on the right side. Next. Neutral surface. Neutral surface. Is the surface whose length remains same even after bending. In vertical bending, default you are considering as nothing is mentioned, we are considering the member as the horizontal member. If nothing is mentioned, we are considering the horizontal member. Then the beams are always horizontal. In vertical bending, neutral surface is the horizontal plane passing through the this is what now vertical bending. Now top surface gets contracted, bottom is elongated. Top surface gets contracted, bottom surface elongated. Then somewhere the length is same. So the neutral surface which plane? Horizontal plane. Top surface horizontal plane, bottom also horizontal plane. Like this, how many horizontal planes are there? Infinite. But which horizontal plane? The neutral surface. In vertical bending, neutral surface is the horizontal plane passing to the longitude axis. It is also horizontal plane. Like this, how many horizontal planes are there? Infinite. So how to identify the neutral axis directly? No. Neutral surface, the horizontal plane passing through the longitudinal axis and vice versa. In horizontal bending, neutral surface, the vertical plane passing to the longitude axis. Vice versa means horizontal bending. Neutral surface, the vertical plane passing to the longitude axis. Next. Neutral axis. Neutral axis is the line of intersection of this definition. Every year I am discussing now, but this was asked once again for the 2021 paper. ESC mains was given now. 2021 is given now. Neutral axis is the line of intersection of neutral surface with the cross section. Neutral axis is the line of intersection of neutral surface with the cross section. So each and every conclusion valid under pure bending, because this equation valid under pure bending. This equation valid under pure bending. This statement is also valid under pure bending only. Each and every conclusion is going to be valid under pure bending. Neutral surface, the line of intersection of neutral surface with the cross section. Neutral axis coincides with centroidal axis in the plane of cross section. Neutral axis coincides with the centroidal axis which is how many central axes are in the plane of cross section? HCA and VCA, but it will coincide with HCA or VCA. How to do it? This is a vertical bending, means it is acting about HCA. Horizontal bending, it is acting about VCA. So neutral axis coincides with the central axis which is in the plane of cross section and about which bending couple, or you can call the bending moment. In vertical bending means vertical plane, means this will be about which axis now? HCA. So it will coincide with HCA. Horizontal bending, horizontal plane means it is about VCA. And starting also you already studied now. Always blindly moment of inertia section modulus about which axis now? Moment of inertia and section modulus should be about a central axis which is perpendicular plane of the couple. This is vertical plane. Couples are in vertical plane. For vertical plane, about which central axis perpendicular? Horizontal. And horizontal plane, which central axis perpendicular? VCA. That is under vertical bending. Under vertical bending, neutral axis coincides with HCA and vice versa. That is horizontal bending, it is coincide with VCA. But all the textbooks they are taking directly HCA, the neutral axis, because they are dealing with the beams are always subjected to vertical bending. What is the meaning of vertical bending? The couples are in vertical plane, or that bending is in vertical plane, or you can see that arc of bending that can be seen in the vertical plane. That is the front view, you can see it now. Next, y. What the y now? Distance of a fiber on cross section distance of a fiber on a cross section from its neutral axis. Distance of a fiber on a cross section from its neutral axis. What the y max now? Distance of faraway fiber from its neutral axis. Generally, which fibers are far away now? Which fibers are far away now? Top and bottom. Extreme fibers are far away. What the I? Integration of y square dA. What is y square dA? What is dA? Elemental area. dA the elemental area located distance of y. dA into y. Force into perpendicular distance, the moment of a force. Force into perpendicular distance, the moment of a force. So dA into y is called as what? A moment of elemental area. Now what the y square dA? Second moment of elemental area. And what this integration will give now? Second moment of the entire cross section. Force into perpendicular distance, the moment of a force. So dA into y. dA the small elemental area located distance of y. So y into dA is what the first moment of elemental area. What the y square dA? Second moment of elemental area about neutral axis. And what this integration will give now for entire cross section. This is representing that only I studied now. Mass moment of inertia and area moment of inertia. In this subject, you are dealing with the area moment of inertia. This is about now second moment of area. Mass moment of inertia is about now second moment of the mass, but this is the second moment of area. This is second moment of elemental area about neutral axis. And what about this total term is representing now? Integration will give what now? For total cross section. What the area of the total cross section A? This is representing, this total term is representing second moment of area of cross section, entire cross section. So what this I is representing now? Second moment of area of the cross section. This only are calling as the area moment of inertia. So overall what the I is representing now? Second moment of area of cross section. This only are calling as what now? Area moment of inertia. Area is the default. So default in our subject moment of inertia means area. Similarly, you are going to get a second moment of the mass. Second moment of the mass is nothing but what now? That you are calling as what a mass moment of inertia. Mass moment of inertia. Now that is about now. This is called as section modulus. Section modulus of section modulus of cross section about its neutral axis. Already I are given the what a generalized definition. Section modulus, what the definition I given now? Section modulus about a central axis equal to numerator. I have to take the moment of inertia about that central axis upon distance of the far away point from that corresponding axis here written now. But most of students are going to tell I by Y. It is not I by Y. I by Y max is a geometrical property. For circular cross section, how much you got it? Na pi d cube by 32. For rectangle, how much you got it? Na BD square by 6 or DB square by 6. Most of students are going to tell I by Y. Next, what is the R now? Radius of curvature of neutral surface, NS. Radius of curvature of neutral surface. Then what the sigma B? Bending stress. Bending stress at a fiber located at a distance of Y. What you have studied under bending, what happens now? Top fiber or more contraction. Means when I am neutral surface, what now? Neutral surface, there is no strain, no change in length. So when I am going to the neutral surface to extreme surface, what happens now? Change in length is going to be increased now. Change in length is increased. When the change in length increase, automatically strain will increase. When the strain increases, stress will increase now. So always at the neutral axis Y is 0. At the neutral axis Y is 0. Bending stress 0. So bending stress is always 0 at the neutral axis. Bending stress at a fiber located distance of Y. Maximum bending stress on the cross section. That is at the fibers far away from neutral axis. Far away from neutral axis, because actually what now? Strain is proportional to Y. By using Hooke's law, we are writing the what now? By using Hooke's law, we are writing the what? Stress is proportional, but actually is what now? Strain is proportional to Y. Longitudinal strain is proportional to Y. strain is what at the neutral axis, neutral surface change in length is 0. Neutral surface change in length is 0. Mean where y is 0. When y is 0, longitudinal strain is 0. So when you are going to the neutral surface to extreme, what happens now? Y will increase. When y increases, what now? Change in length increase. When the change in length increases, strain will increase. Longitudinal strain increase. Then stress is going to be increased. Longitudinal strain at a surface located at a distance of y from neutral surface. Longitudinal strain at a surface located distance of y from neutral surface. Maximum longitudinal strain. That is the longitudinal strain at the surface far away from neutral surface, because it's completely chapter number 5, where once again when you are going for there, I'm not going to discuss all this terminology now. We directly are going for the problems now. Somebody will ask now, sir, when you are not discussing the bending, sir, why you are because this is required for even in SFD BMD. SFD BMD is required. SFD BMD is the third chapter now, and is also required in the first chapter. First chapter there are some questions on eccentric axial load. Eccentric axial load equal to one axial load and one bendiment. So when you are doing the bendiment now, we need this. All these calculations are required now. There is some logic is going to be there. Why I am discussing now. That's why what the bending stress what now varies linearly. For the axial stress variation, you got a rectangle. But bending stress what a 0 at the neutral axis maximum. Therefore, bending stress what a variation will be a triangle. Bending stress will vary linearly. Bending stress what a 0 at the neutral axis, maximum at the extreme fiber. So neutral axis to extreme fiber, it will vary linearly. Analysis of the bending equation. Analysis of bending equation. So how many ways you can analyze this equation? If I'm calling this term A, and this is B. So A is equal to B is equal to C. So you can equate A and B, B and C and A. If we equate A and B, if we equate A and B, what the aim of the strength of material studied now? There are the expression for stress, strain, deformation under different loading now. A is equal to B, B is equal to C. Then from this one, what you are getting now? If we equate A and B. From this one, what you are getting now? Sigma B is equal to sigma B equal to my by I, my by I. So with this one, now you can find out the bending stress at any fiber. Fiber to fiber, which one will change? Now Y will change. Similarly, if we equate B and C, so both the equations are going to give the same value now. Both are giving the what? A bending stress. Already I written the terminology. But the sigma B are written a bending stress at a fiber located distance of Y. So what these both the equations are giving now? Bending stress at a fiber located distance of Y. But shall I use the first equation or second equation? If I know the bendiment, I have to go for the first equation. If I know the radius of curvature, then you have to go for the second equation. When a belt is going or a pulley, belt is subject to bending, elastic bending. We are all dealing with the elastic. So you can use any equation, but mostly theoretically, which one is known? Bendiment is known. But some question, we know the radius of curvature of the neutral surface. When a belt is going or a pulley, belt is what? A bend moves over a pulley subject to bending, elastic bending. In that case, you know the radius of curvature. So both will give the bending stress at a fiber located distance of Y. If you know the bendiment, you are going to the first equation, and this is what now? When you know the radius of curvature. So this equation should be used when you know the bendiment on the cross section. The equation should be used when you know the radius of curvature of neutral surface. Radius of curvature of neutral surface. But always for design, you are interested in what now? Always for design, you are interested in maximum stress now. Maximum stress. From equation 1 and 2. From both this equation, what you can tell it now? For a given cross section, for a given cross section, bend moment is same. Moment of inertia constant, E is same, R is same. So that's why bending stress proportional to Y. So bending stress will vary linearly. Bending stress, the ratio of top fiber to bottom fiber equal to Y top to Y bottom. So this ratio is what now? This ratio will be 1 or more than 1 or less than 1 or equal to 1 now. Equal to 1 if centroid is exactly what now? Centroid is exactly the mid depth. This ratio will be 1. Circular, square, rectangular. This ratio will be what now? 1. Triangular, this ratio is 2. Triangular centroid will be what now? Triangular centroid will be what now? At a distance of h by 3 from the bottom to h by 3 from the top. So if we go for triangular, what the y top now? 2h by 3, y bottom is h by 3. Then this ratio is what the more the 2. So when centroid is exactly at the mid depth, this ratio will be 1. But which cross section centroid is exactly at the mid depth? Circular, square, rectangular and symmetric eye section. But a T section centroid is not exactly the mid depth. Triangular also not exactly the mid depth. For square, rectangular, circular eye section, for all this cross section, this ratio will be 1 because centroid is exactly the mid depth. Neutral axis coincide with which axis now? HCA. Horizontal central axis. Neutral axis coincide with what now? HCA in case of vertical bending. So default you need the neutral axis location. Neutral axis location means we need the HCA. HCA means horizontal central axis. Mean we need the centroid. So for all this case centroid is exactly the mid depth. Then Y top and Y bottom are same. But if we go for a triangular, default you are taking the HCA, the neutral axis, because of what now? Vertical bending. Default you are discussing for a beam. Beams are always vertical bending. Vertical bending, neutral axis coincide with HCA. So this will be what a Y top. This is a Y bottom. So what this ratio now? 2. If you go for a T section centroid is not exactly the mid depth. T section, centroid is not exactly the mid depth, centroid is near to top. This line is about a top fiber. All this top fiber, bottom fiber, everything you have studied starting only is the bottom. So this will be the Y max. In this case, which is the Y max now? So in case of triangular section where the bending stress maximum not top, but T section where the bending stress maximum at the bottom. What the Y max you have studied now? Y max is the distance of a far away fiber. If Y is more means bending stress is more. So in this case, what this ratio now? Less than 1. So where the bending stress maximum, everybody is going to mention top and bottom. Top and bottom is maximum only when the centroid is exactly at the mid depth, that is circular, rectangular, square and symmetric eye section. Centroid is exactly at the mid depth. So bending stress at the extreme fiber is equal. But in this case, bending stress maximum at the top. In this case, bending stress maximum at the bottom. Now, in one of the paper also asked now, a triangular, a cantilever beam having a T shape now. A cantilever beam having a T cross section, bending stress maximum, top, bottom, neutral axis. This is what a neutral axis. Neutral axis coincides with HCA. But when this will coincide with the HCA, in case of vertical bending, in horizontal bending, it will coincide with VCA. So if somebody will ask where everybody is going to mention bending stress maximum at the extreme fiber, that is what now? Correct only when the centroid is exactly at the mid depth. So where the bending stress maximum means what the answer now? Bending stress maximum at the fiber far away from the neutral axis. In these 3 cases now, 4 cases where the which fibers are far away, both top and bottom. In this case, which fibers are far away from the neutral axis top. In this case, which fibers are far away from the neutral axis bottom. Next, we want to get a maximum bending stress. Maximum bending stress. To get a maximum bending stress, what a bending stress proportional to y. So in this equation, what should I substitute now? Y max, you have to substitute it now from equation 1 and 2. So this is what now? This only are called the section modulus. Section modulus. M by Z. That only somebody was asking about the significance of the section modulus. More section modulus means less bending stress. So always which section is better now? Which is having the more section modulus. Which is having the more section modulus. Non-circular section will give the more section modulus. Non-circular section will give the more section modulus. For a given area, non-circular section will give the more section modulus. That's why never beams are circular now. There are three beams, all are subjected to same bendiment. There are three beams, all are subjected to same bendiment, but they are having the different cross section. One is a circular, one is a rectangular, high section. Now, which is the better means which is having the more section modulus. Higher the section modulus means lower the bending stress. Then chance of failure are going to be less. Now, when stress induced is less, means chance of failure are going to be less. If you ask the most of students which is the best section, means directly they are going to tell I section. Every time directly we cannot mention the I section now. Which section the best means what now? Which is having the higher section modulus. But for same area, I section will have the more section modulus. But without knowing the area, we cannot tell it now. If you ask the 100 students now, which section the best section means directly they are going to tell I section. That answer is correct when all are having same area. So if when you don't know area, we cannot directly conclude it now. So what the answer here to which is the best section means which is having the higher section modulus. So always in the beams, best cross section, the cross section which is having the higher section modulus, higher section modulus. Then you can make a conclusion. Sir, for a given area, I section will have the more section modulus. Then I section the best now. But when the areas are different, we cannot directly conclude it now. Now this here written from which equation? Now from 1. That only starting here what you have studied now. Stress always independent of the material. Stress directly proportional to corresponding load, inversely proportional to corresponding geometrical property, independent of the material, independent of the material. Always stress on the cross section is what? A stress on the cross section. How many stress are on the cross section? 4. Axial, bending, torsional shear, direct shear. They're all what? Now, independent of the material, except under which case you have studied now 3. What are they now? Sulfate example, impact loading, as well as what now? Thermal stresses now. Except 3 condition remaining, all the case what now? Stress on the cross section, the independent of the material. Similarly, from equation 2. From equation 2. Both will give the same value. Both will give the same value. But shall I use the equation 4 or 5? Anyone you can use it now. But when bendment is given, use the equation 1. When radius of curvature known, use the equation 5. Equation 5. As per the given data, you have to select it now. As per the given data, you have to select it now. Now, next question is, Shall I need the equation 1 is required, 2 is required, 4 is required, or 5 is required? 1 is required, 4 is required, or 2 is required, or 5 is required? Any one is sufficient now. If I know bending stress are one fiber, remaining all are what? Linearly varies. So what the advantage of bending stress now? If I know the bending stress one fiber, remaining all you can directly can calculate it now. Equation 1 upon 4. Equation 2 upon pi. What you are getting now? Sigma b by sigma b max is equal to y by y max. Y by y max. So what the conclusion here now? So equation 1 is required or 4 is required? Any one. If I know the bending stress on one fiber, remaining all you can find out directly now. If I know the bending stress at a fiber at distance of y, directly can find out the maximum bending stress. So 1 is required or 4 is required or what? Any one is sufficient. Any one. If I know this value, how to find out that now? By using this equation now. How we got it now? Bending stress what varies. Bending stress the normal stress or shear stress? Bending stress the normal stress. Bending stress the normal stress. Normal stress means what? A perpendicular to cross section. Axial bending stress are what now? Perpendicular to cross section. Which axis perpendicular cross section? HCR, VCR, polar axis. HCR, VCR, polar axis. So always the axial and bending stress are in which direction now? In which direction? Bending stress and axial stress is what now? In x direction or y direction or z direction? What the answer now? Axial and bending stress are always in the direction of the polar axis. In the direction of the polar axis. In the direction of the polar axis. If the polar axis is going to be x-axis, if the polar axis is x-axis, then it will become as what? X. If the polar axis is y, it will become as a y. So this is a cross section. This is a cross section. This will be what now? Top fiber, bottom fiber. This is the neutral axis. Bending stress is always perpendicular to the cross section. Now, bending stress what now? Here I am assuming the centroid is exactly at the mid depth, d by 2, d by 2. So always the bending stress variation comes off. Here bending stress 0. Here to here how it is increased now linearly. So bending stress variation comes off two similar triangle. But what about the axial stress variation you have studied now? Rectangle you have studied. But here you are going to get the two similar triangles. Maximum at the bottom now. And here to here how it is varies now. Linearly varies. Linearly varies. Always what the bending stress variation consists of two similar triangles. Are the identical triangle or unidentical triangle? They are identical triangle when y top and y bottom are same. Y top and y bottom are same. But in triangular, they are not identical triangle because of what now? Y top and y bottom are not same. Y top is triangular 2h by 3. Y bottom is h by 3. So bending stress variation consists of two similar triangles always. But they will become as the identical triangle when centroid is exactly at the mid depth. That is circular, square, rectangular and symmetric isection. Here these are the two similar triangle, means I taken what this d by 2, this d by 2. Centroid is exactly the mid depth. Now what this line is representing now? Cross section. Not the perpendicular to cross section. For a cross section which axis perpendicular. For a cross section which axis perpendicular polar axis. So I have taken this the polar axis. Now what is z axis now? This line is a cross section for a horizontal member. Horizontal member. This is what now? This is a cross section. In the front view, this will become as a vertical line where you can see the cross section in the side view. So this will be which axis now? Polar axis. So now this will become as sigma z or sigma x or sigma y. Sigma z. Everybody is going to tell sigma x now. When it is a sigma x, if I consider polar axis, x axis. What about this axis now? This is VCA. Neutral axis always coincide with the centroid. Neutral axis coincide with the centroid. Where you can see the fibers, always fibers can be seen in the. This is what now? Fiber. They're all the fibers. So all these fibers where you can see it now, like this. But when a cross section is like this, for a horizontal member, what? A horizontal member cross section in what now? Profile plane. This is a profile plane. Now this marker is what now? Fiber. So where you can see this fiber now? This fiber can be seen in the plane of cross section. Now all these lines can be seen in side view. But front view, what happens? They are all become as a dot. So all these dots are what now? They're all the fibers. So many times you have studied now. Fibers can be seen always in the plane of. This is about a cross section. All these lines are the fibers. Top fiber, bottom fiber, inner fiber now. But all these fiber can be seen in the plane of. If the cross section is like this, you can see in the front view. But when the cross section the vertical plane, when a member is perpendicular board, but mostly beams are horizontal, cross section a profile plane. So all these fibers can be seen in the side view. But this is a fiber. But in the front view it become as a dot. So all these dots are represent the fibers. Is the top fiber, this is the bottom fiber, these are all what the inner fibers. Now this is what now? Neutral axis. Neutral axis coincide with HCA. This line is the HCA. HCA can be seen in what now? Side view. Central axis can be seen in what now? HCA and VCA can be seen in the plane of cross section. Now this will be which axis now? This is what now? VCA. This is ZX. Polar axis VCA and HCA. Now this is neutral axis. What is the polar axis definition? The polar axis is going to be what now? Central axis perpendicular to cross section. All the basics are discussed now. But if you are not focused on the definition basics, it is difficult to understand it now. If you ask the most of students, bending stress in which direction? X or Y or Z means what now? Somebody is X, somebody is going to be Y, somebody is Z. What the answer now? Bending stress is perpendicular to cross section. For a cross section, which axis is perpendicular? Polar axis. That's why always axial and bending stress are in the direction of the polar axis. If the polar axis Z axis, then this will become as a sigma Z. Sigma Z. If I had taken the X, then it is going to be a sigma X. So what this figure representing now? Bending stress variation. The bending stress variation consists of two similar triangles. But here I am getting an identical triangle because of y top and y bottom are same. This distance here calling as what now? Y top. This is bending stress variation. On a cross section of beam. So here y top and y bottom are same. I am getting a similar triangle, identical triangles. But if you go for a triangular section, this will be 2h by 3. This is h by 3. Then they are not the identical triangle. If somebody will ask, the bending stress variation consists of two similar triangles, two identical triangles, both similar and identical. What the answer now? Similar triangles. Identical triangle is what? When it is valid now? When centroid is exactly the mid depth. But if you go for a triangular and T section, they are not identical triangles. So now this will be called as what now? Maximum bending stress. Maximum bending stress. This is sigma Z. What the equation for this now? M by Z. What the other way you can calculate now? E y max upon R. Sigma Z. M by Z. E y max upon R. E y max upon R. Or what the other way can write down a sigma b max now? Sigma b into y max by y. Next, what about this fiber now? This is a inner fiber. What this distance now? Y. So this is sigma b. This is sigma b. Now to get it, now by using the similar triangles. This is a triangle. One blue color triangle. Then you are getting so from these two similar triangle, one blue color triangle, one red color triangle. Blue color and red color triangle. For a this red color triangle, what the base now? Sigma b. What the height now? Y. So sigma b by y equal to sigma b max upon y max. How we got this relation? By using the similar triangles only. This is one triangle. This is sigma b max. This is y max. This is sigma b. So by using the similar triangles only got this relation now. Sigma b by y is equal to what the advantage of this now? If I know the bending stress at one fiber, remaining all the fiber directly can calculate now. If I know the bending stress at one fiber, remaining all the fiber directly can calculate it now. So once I'm mentioning the bending stress variation consists of two similar triangles, but they will become the identical triangle when centroid is exactly the mid depth. That is when y top and y bottom are equal. When y top and y bottom are equal, the two triangles are identical triangle, but centroid will be exactly the mid depth, circular, square, rectangular and symmetric eye section. But triangular and SD, triangular as well as T section, triangular and T section, centroid is not exactly the mid depth. Then you are going to get a simply two similar triangles, but they are not identical triangles. Now, this is corresponding to sagging or hogging now. This is a tensile or compressive. This is what once again maximum bending stress. Sigma B max. Now this is a tensile or compressive. This stress is a tensile or compressive. Out of these two, now which one is the tensile and which one is the compressive? Shall I take this a tensile or this a tensile? Top one is a tensile or bottom one is a tensile? One is a tensile means automatically other one is a compressive. Always what a bending case, what happens now? One side contraction, one side elongation will be there. So bending stress extreme fibers are what now? Bending stress extreme fibers are what now? Unlike in nature. Top fiber compressive means bottom fiber is going to be tensile. In case of sagging, top is contraction, bottom is elongation. So bending stress extreme fibers are what now? Unlike in nature. But if you go for hogging, what happens now? Top is elongation, means bending to the top is a tensile, bottom is going to be compressive. Now, out of these, which one is the tensile and which one is the compressive? Depend upon the cut surface. If you cut it, how many cut surface will be there now? When you are studying now stress concept, when you cut it, one cut surface on the right side, one cut surface on the left side. Timing, if I am assuming the what now, this is on the cut surface on the right side. If you cut it, how many cut surface are going to be there now? What about this line now? This line is the cut surface on the right side. And what about this line now? Cut surface on the left side. Now for this one, tensile means which side? Now left side. Tensile means away. So if I am assuming this line is about now, this surface now. So this will be a tensile. Now what about here now? For this one, tensile is what? A tensile stress away. For the black color line, tensile will which side now? Left side will be there or right side? Here tensile is right side. Here tensile is what? The left side will be there. So this is what the answer now? Is it tensile or compressive mean what the answer now? If I assume this cut surface on the right side, if you assume the cut surface on the right side, this is what now assuming the right side, then tensile will go which side now? Left side. So this is a tensile. Means the hogging or sagging now? Hogging. Hogging case, sorry, sagging case, sagging. Sagging case, bottom is going to be a tensile. So this corresponds to sagging when cut surface on the right side. Suppose I am assuming this cut surface on here on the left side. Left side means tensile, which side? No, right side. This will be a tensile. If you assume this cut surface on this left side, this is a tensile. When you are going to get a tensile at the top now, hogging case. So the sagging or hogging mean what the answer? Both are going to be correct now. If I assume this going to be on the right side, if you assume this cut surface on the right side, it is correspond to sagging. Sagging. If it is the right side means this is a tensile. In case of sagging, bottom you are getting a tensile. Bottom you are getting a tensile. And if you assume this cut surface on the left side, this is a tensile. When you are going to get a tensile now, when you are going to get tensile at the top now, hogging case top is what? A tensile. Here tensile will which side now? Here tensile will which side now? Right side. Tensile will be right side will be there now. Here tensile will be left side. It is also tensile, it is also tensile, but this is what a tensile on which side now? Right side. Is a tensile on the left side. So if somebody will ask now, if it is going to standard question will be there now. This bending stress variation corresponding to sagging or hogging. What the answer now? If I assume this cut surface on the right side, if you assume the cut surface on the right side means what now? Always tensile stress away. Right side away means which side now? Left side. Therefore this will be a tensile. When you are going to get a tensile at the bottom now, under which bending you are going to get a tensile at the bottom? Hogging, sir, sagging. Sagging case what happened? Top is contraction, bottom is elongation. And if you assume this cut surface on the left side, then this is a tensile. When you are going to get a tensile at the top, now hogging case, bottom is contraction, top is elongation. So what the answer you had right done now? This variation corresponds to sagging. This variation corresponds to sagging when this cut surface on the right side. And this variation corresponds to hogging when the cut surface on the left side. Tensile stress towards left side, right side, both are correct now. If cut surface on the left side, tensile means what the answer now? If it is going, somebody is going to say the left side and right side, we cannot tell it now. Tensile stress is stress away from the cross section. When the cut surface on the left side, away means which side will be there now? Right side. This is going on the right side. So this will become the tensile when cut surface on the left side. And when cut surface on the right side, tensile means away, left side. So tensile to the left side or right side mean both are correct now. On the right side, tensile stress will be left side will be there. On the left side, tensile stress will be on the right side will be there. The above bending stress variation above bending stress variation corresponds to corresponds to corresponds to sagging bending when cut surface is on right hand side. For right hand side, tensile will which side? Now left side. Right hand side tensile will be left side. Now this is a tensile. I'm getting a tensile at the bottom. When you are going to get a tensile at the bottom, now in case of sagging, sagging top is contraction, bottom is elongation. It corresponds to hogging bending. When cut surface is on left hand side. When a cut surface left side means tensile will be right side. Right side. Now this stress on the right side. So this will become the tensile when cut surface the left side. So when you are going to get a tensile at the top now, in case of hogging case what? The bottom is contraction, top is elongation. If this question was asked so many about 9 students, randomly they will tell, sir, the sagging, hogging, maybe a sagging, hogging, they are going to give the random answer, they are going to give it now. Now, can you give the state of stress now? Can you give a state of stress? If I am going to take a point, how to take the state of stress? How to take the state of stress? Is a point. Take a small elemental cube. Now, anybody, what about this stress now? Either which phase it is now? Anybody now? Is a Z phase. This line is about a cross section. Now, cross section of which phase now? Z phase. Z phase. On Z phase, how many stress are there now? Tau Zx, sigma Z, tau Zx and tau Zy. Now this is sigma Z. And what about this stress now? What this hand is written parallel, tau Zy. And what about this now? Tau Zx. This finger is what? A tau Zx and this is tau Zy. Shear stress what a parallel now. This is what now parallel tau. Parallel to which face? Z face. Along which direction? Y. Tau zy. And what about this finger now? Tau zx. Tau zx. But here, how many stress I am getting now? Under pure bending what now? On every cross section you are getting only bending. Means you are getting only bending stress. Means there is no tau zx and no tau zy. Only you are getting sigma z. That's for the uniaxial state of stress. On a cross section what now? Shear stress 0. Pure bending case what? When you are going to get a shear stress in a cross section, whenever you want to get a shear stress on a cross section, there should be a twisting or there should be a shear force is required now. But the pure bending case, there is no shear force, no twisting. So there is no shear stress. So which stress is 0 now? Now you can see now, we are getting only normal stress. Why? The pure bending case, there is no shear force, no twisting. When there is no shear force, no twisting, there is no shear stress. So this stress is what now? Tau z x, tau zy. This is tau zx. Both are 0. So here you are getting overall how many stress now? Only one stress. Which stress now? Sigma z. That's for the uniaxial state of stress. That's why I clearly mentioned now. What the example starting you have discussed now? What the example for uniaxial state of stress means? Pure axial loading and pure bending. Pure axial loading and pure bending. Now if I take a small elemental cube, which point I have to consider now here? Which one is the critical point? Always stress analysis where you have to do it now. Stress analysis should be done at the critical point. Critical point is the point where all the stress are maximum now, where the bending stress maximum now. So in case of pure bending, which one are the critical points now? In case of pure bending, which one is the critical point in a cross section? The point far away from the neutral axis now. Always the stress analysis should be done where now? At a critical point. What is the critical point now? Where resultant normal stress, resultant shear stress. But in case of pure bending, there is no shear stress. Tau d is 0, tau max is 0, tau t is also 0. Pure bending means only bending stress will be there. Axial stress 0, direct shear 0, torsion. Out of the 4 stress, how many are 0? No? 3 stress are 0. Only 1 stress is there. So directly, which one is the critical point? At which point bending stress maximum? So which one are the critical point in case of pure bending now? The points far away from the neutral axis. Which points are far away here? No, top and bottom. Because I have taken the y top and y bottom are same. But if you go for a triangular section, which one are the critical? No? Point on the top. But if you go for a T section, which one are the critical? No? Bending stress maximum at the bottom. But when centroid is exactly the mid depth, then y top and y bottom are same. Then bending stress top and bottom is same. So in that case, which one are the critical points now? Any point on the top fiber or any point on the bottom fiber. But in case of triangular section, which one are the critical points now? Any point on the top fiber. T section, which one are the critical point? Any point on the bottom fiber is the critical. Now I'm going to take about now how to define the state of stress you have studied now. Take a small elemental cube. Small, now this is which face now? Is which axis now? X axis. This is which axis now? X axis. This is X face. What about this now? Is a Z face. Mean nothing but a cross section, Z face. Now this is what now? This stress acting perpendicular to which face now? This face. This is sigma Z. There is no stress on this now. X face there is no stress. Y face there is no stress. And Z face we are getting only sigma Z. What about this stress now? Tau Zy, tau Zx. Y both are 0 now. When you are going to get a tau Zy and tau Zx. Whenever you want to get a tau Zy and tau Zx. Tau Zy means Z face means what? A cross section. This is nothing but a cross section. Cross section I have taken a Z face. So when you are going to get a tau Zy and tau Zx, when you are going to get a shear stress in the cross section, whenever you want to get a shear in the cross section, there should be a shear force or twisting. But the pure bending, under pure bending, shear force 0, twisting is 0. So shear stress in the cross section 0 means on Z face which one is 0? No, tau Zx 0, tau Zy 0. Only which stress is there now? On a Z face you are getting 3 stresses, sigma Z, tau Zx, tau Zy. but pure bending, we are getting only bending. Due to bending, what? You are getting a bending stress. Bending stress is the normal stress. So you are going to get only sigma z. So this stress is what? A perpendicular to which face? Now this now. Now if I can take this cube outside now, if I take this cube outside, this is bending stress, sigma z. This here taken as which face now? Z. So this is nothing but the cross section or Z face. What about this now? X, Y. So total how many stress are going to be there now? Here there is no stress, only you are getting sigma Z. This is what? A tau ZY. This is tau Z, both are 0. When you are going to get tau ZY and tau ZX, whenever you, Z face is but a cross section here now. So to get a tau ZY and tau ZX, what is required now? Either there should be a shear force or there should be a twistment. Suppose that twistment is there, what you have studied now? Due to twistment, you are going to get a torsional shear stress. Then you are going to get tau ZY or tau ZX is going to be there now. That's why you have studied the pure shear state of stress now. Then automatically for equilibrium, what you are going to get it now? It is a uniaxial state of stress. What is this figure representing now? State of stress at any point on top fiber. How many points are there now? Infinite points. Any point on top fibers. Top fiber of a beam under now this becoming the tensile now. This becoming the tensile. So when this will become the tensile now, when you are going to get a tensile at the top, hogging, pure hogging bending. So overall it become the uniaxial or biaxial or triaxial? Uniaxial. How many stress are 0 now? Sigma Z is equal to sigma B max, sigma X, sigma Y, and tau XY, tau XZ, but if you go for bottom, what happens now? Top is a tensile. Hogging case, top I am getting tensile. Bottom, what you are going to get? A compressive. Bottom will become as a compressive will be there now. Uniaxial state. Directly this will become as a principal plane. Principal plane. Now can anybody give the what the maximum shear stress at the top fiber? What the maximum shear stress at this point? Uniaxial case, what the maximum shear stress? Half of this now. Everybody is going to tell, sir, shear stress 0. Shear stress 0 on the cross section is 0. But if we ask at this point, what the maximum shear stress now? Under uniaxial state of stress, what the maximum shear stress? Half of sigma x. So what the maximum shear stress at any point on the top fiber now? This is a principal plane, the principal plane is a sigma 1 plane. is a sigma 2 planes. This itself directly what a sigma 1. Uniaxial state of sigma 2 and sigma 3 0. Then where you are going to get a tau max plane at 45 and 135. Uniaxial case what the sigma tau max na sigma by 2. So once again here you should be careful now. If you ask the most of student now, what the maximum shear stress in the beam? Sir, 0 sir. Pure bending, there is no shear force sir. No twistment, therefore shear force 0, shear stress 0. On the cross section is 0. But if you ask in the beam means what? You have to consider all the planes. All the planes. It is a uniaxial state of stress. Uniaxial state of stress. When you are studying about a bar subjected to pure axial loading, you are getting a uniaxial state of stress. Cross sectional principal plane, tau max planes 45 and 135. So what the answer now? What the shear stress on the cross section means? Answer is 0. What the shear stress on the cross section is 0. But what the shear stress in the beam? Maximum shear stress in the beam means what the answer now? Half of sigma b max, that is half of m by z. Half of m by z. So thank you, my dear friend, Mr. Swaraj. Suppose if I not explain the word of principal stress chapter now, here I cannot explain the word now. This concept I cannot explain now. Then I will tell it what directly shear stress 0. But if you ask this question now, what the shear stress in the beam means what now? If it is going to give the 0 now. Sir, you have mentioned pure bending, there is no shear force, no twistment. When shear force and twistment is 0, the shear stress 0, sir. Whatever you have studied, the shear force, twistment, bending moment, axial load, they are on the cross section. On the cross section is 0. On Z phase is the cross section. But ask in a beam. In a beam means you have to go for the all the planes. But where you are doing a critical point, this is a critical point now. Always what the critical point you have studied, a critical point is a point on a cross section. Critical point is a point on a cross section where resultant of axial and bending, resultant of torsional shear and direct shear. But here torsional shear 0, direct shear 0, axial stress 0. Only one stress is there, bending stress. So directly which one the critical point? Critical points are the point far away from the neutral axis. In this case, which one are the critical? Top and bottom are critical. Since I was in this hogging, I was in this a tensile now. So what the maximum shear stress in the beam? Maximum shear stress on the cross section is 0. But what the maximum shear stress in the beam? Half of m by z, sigma b max. Half of sigma b max. This will be at what angle now? This will be on the cross section means, but this will be at what angle now? 45 and 135 degrees now. 45 and 135 now. Now this leads to what now? Uniaxial state of strain or triaxial state of strain. Uniaxial state of stress leads to triaxial state of strain. Due to this one, you are getting longirus strain. In this direction, longirus strain. Other two direction, what you are getting, the lateral strains are there now. Always under uniaxial state of stress, you are going to get a triaxial state of strain. State of stress is uniaxial, but state of strain is a triaxial. In this direction, what the stress? Strain, longirus strain. This strain is what? A longirus strain. Lateral strains are there. Now, this is what a sigma z means epsilon z will become the longirus strain, and epsilon x and epsilon y the lateral strain. Every longitudinal strain associated with the lateral strains. Epsilon Z will become the longitudinal strain, but the stress tensor size now 1 by 1 matrix. Stress tensor is a 1 by 1 matrix, but strain tensor is what now 3 by 3 matrix. 3 by 3 matrix. Only diagonal elements will be there now. Epsilon X, Epsilon Y, Epsilon Z. Under uniaxial state of stress, you are going to get a triaxial state of strain. The strain in this direction is Epsilon Z, that's the longitudinal strain. And other two direction, we are going to get a lateral strains are going to be there now. Now this variation valid for which cross section now? This variation is valid what now? So cross section to cross section, what happens now? This shape will not change now. Cross section to cross section, which one will change now? I taken two identical triangles because of centroid is exactly mid depth. If you go for a triangle, what happens now? They are not identical triangles. So this is valid for any cross section, whether you go for a T section, I section, or circular or rectangular. Always about the bending stress variation consists of two similar triangle, but they will become the identical triangle when centroid is exactly the mid depth. So bending stress variation. Bending stress variation consists of for any cross section consists of two similar triangles, but they will become the identical triangles. Good, Mr. Vaibhav is given good answer now. Good. I am giving my efforts, I am putting my efforts now. But who is going to believe the teacher, believe the himself now? And who is going to struggle it now? Who is going to struggle it? 90% they will what understand now. 10% they will not follow it now. Means the 90% they are following means what now? They have put the right action. They have believed the teacher. They have believed themselves. They have sacrificed and they have done the right action. But remaining 10% they are not following means what now? They have not done the right action now. Completely subject they interrelated. Completely subject they interrelated. That's why I'm going to tell it. If anybody is getting a success means what now? The credit goes to that friend only. We are doing our role. That is what our role is what MEDIZ and teacher's role is 40 to 50% now. If anybody is getting a single digit rank means the credit goes to that friend only. Definitely MEDIZ and teacher role is there now. But that friend is what now? He has struggled like anything now. So bending stress variation consists of two similar triangles, but they will become the identical triangle what now? When centroid is exactly the mid depth. And the last one is what now? By equating what the last one now? Equating the last A and C. If you equate A and C, M by I is equal to E by R. So from this one what the R now? EI by M. With this equation, we can calculate the what? This will be called as what now? Equation 7. Equation 7. This is used to find out the radius of curvature. Used to determine radius of curvature of neutral surface. used to find out the radius of curvature of neutral surface. Now can you find out the longitudinal strain now? Maximum longitudinal strain. Now it is a uniaxial or biaxial state of uniaxial. Then I can use the Young's modulus concept can be used now. Young's modulus valid under uniaxial state of stress. So you can use the Young's modulus. What the Young's modulus? Now sigma by longitudinal strain. Then how to get a maximum longitudinal strain? Sigma B max upon E. Maximum longitudinal strain. Sigma B max upon E. What the sigma B max now? M by Z E. Or what the other equation now? Y max upon R. What the sigma B max now? E Y max upon R. So E will get cancelled out. Then you are getting Y max by R. When the Young's modulus definition valid now, uniaxial state of stress. Under uniaxial state of stress, what you studied now? Young's modulus is the ratio of normal stress to longitudinal strain. Then how to get a longitudinal strain? Normal stress upon Young's modulus. That is the sigma B max upon E. What the sigma B max? M by Z upon. But if what the other way you can write on the sigma B max E Y max upon R. E will get scanned. Then you are getting the Y max upon R. So this completes the total bending equation now. Now almost all the questions you can answer it from this now. All the questions you can answer it. Most of the questions you can answer it now. Chapter number 5 is a bending stress equation. One more equation is there, shear stress now. So far I discussed only the how to find out the bending stress now. So today's lecture is completed. We'll continue tomorrow. So tomorrow directly I'm going for the what now? We are coming to the first chapter. We are going to draw the how to complete the bars in series and the parallel ALD. Then we'll come to the SFD BMD. But these are all required when you are going to the first chapter. That's why I discuss all this thing. So almost this, with this one chapter number 5, 70% of the chapter number 5 is completed. Only 30% is left out. Only shears and the beam calculations are required now. So can you refer the workbook now? I will give the answer questions. So if somebody will ask how many example for uniaxial state of stress mean what? Pure axial loading and pure bending. But what's the difference between pure axial loading and pure bending? Try to write down this difference. I'm going to discuss. Pure axial loading and pure bending. What's the similarity in pure axial loading and pure bending? Similarity is what now? Already starting you studied pure axial loading and pure torsion, you studied it now. Pure axial loading and pure torsion, you studied it now. Similarly, now you can prepare a what now? Already I completed the pure torsion and pure axial loading. Importance almost 12 or 13. They're based upon so many conclusions were there now. Similarly, now pure axial loading and pure bending. Pure axial loading means ALD is a rectangle. SFD, BMD, TMD is a line cones 0. Pure bending means BMD is a rectangle, SFD, ALD, TMD are line cones 0. In both the case, uniaxial state of stress. In both the case, uniaxial state of stress. Now, what is the difference now? Axial stress variation. Axial stress are uniformly distributed or non-uniformly distributed? What the axial stress variation is studied now? Rectangle. Axial stress are uniformly distributed. That's why you have written P by A. So what the third difference now? Axial stress are uniformly distributed. At each and every point, axial stress same. Third difference is what now? Axial stress are uniformly distributed, but bending stress are varying linearly. Bending stress are varies linearly from fiber to fiber. Next, what the shape of the axial stress variation? Rectangle. What the shape of the axial stress variation? Rectangle. But bending stress variation consists of two similar triangles. Two similar triangles. Next, axial stress are like in nature. When I'm going to pull it, all are tensile. When I'm going to push it, all are compressive. So axial stress are like in nature. Maybe a tensile or maybe compressive. If I'm going to pull it everywhere, I'm going to get a tensile stress only. If I'm going to push it everywhere, I'm going to get a compressive. But what about the bending stress now? One side you are getting a tensile, one side you are getting a compressive. Above neutral axis a tensile means below neutral axis a compressive. In case of sagging, above neutral axis a compressive. Below neutral axis a tensile. Hogging case, above tensile and below is the compressive. Next, what is the other one now? There is no neutral surface. No neutral surface and no neutral axis in case of axial loading. When I'm going to pull it, all are elongated. Everywhere the elongation is same. Mean there is nowhere change in length is zero. So in case of pure axial loading, there is no neutral surface, no neutral axis. When there is no neutral surface, means what? No neutral axis will be there. But pure bending, what happens now? Neutral surface exists and neutral axis will exist. And the neutral axis will coincide with the either HCA or VCA. These are the difference. Quickly, I'm going to repeat it now. Now you can once again prepare this table now. Left side, I'm taking the pure axial loading. Right side, a pure bending. What the first difference now? Under pure axial loading, ALD the rectangle, SFD, BMD, TMD are the line coincides zero. Pure bending, BMD the rectangle, ALD, listen, you can write down after. ALD, SFD, TMD are line coincide zero. What the next now? Axial stress are uniformly distributed. Axial stress are uniformly distributed. Means at each and every point on the cross section, axial stress same. That's why you are written P by A. Bending stress varies linearly. Fiber to fiber, they are varying linearly. Next, axial stress variation. What the shape of the axial stress variation? Rectangle. But bending stress variation consists of two similar triangle. Next, axial stress are like in nature. Means axial stress are completely tensile or completely compressive. When I'm going to pull it, completely tensile. When I'm push it, completely compressive. But what about the bending stress? Bending stress are both tensile and compressive. Above neutral axis compressive means below neutral axis is going to be tensile will be there. So bending stress are both tensile and compressive. Next, under pure axial loading, no neutral surface, then no neutral axis. There is no neutral axis, no neutral surface. When there is no neutral surface, there is no neutral axis. Neutral surface means what? Change in length should be there. When I'm going to pull it, all are equally elongated. Therefore, under pure axial loading, no neutral surface, no neutral axis. But pure bending, neutral surface will exist and neutral axis will exist. The neutral axis will coincide with the what now? Either HCA or VCA. In vertical bending, it will coincide with HCA. Horizontal bending, it will coincide with VCA. But what is the similarity in both the cases now? Both are normal stresses. What is the similarity in both the case? Axial and bending stresses both are normal stresses. Mean both are in the direction of the polar axis. Axial stress and bending stress both are normal stress. Means perpendicular to cross section. That is they are in the direction of the polar axis. Both axial and bending stress are in the direction of the polar axis. Next, what is the other similarity? Uniaxial state of stress. Under pure axial loading and pure bending, you are getting a uniaxial setup. There are 5 or 6 differences are there, but similarity are 2 are there. Pure axial loading, pure bending is a uniaxial state of stress developed. Next, both axial and bendings are perpendicular to cross section, that in the direction of the polar axis. That's why both can be added now. Directly both can be added. Both are tensile means you can add it. Sigma A plus sigma B max. But axial is tensile, bendings is compressive. Then what the resultant stress? No, sigma A minus sigma B max. So what the resultant normals in the cross section? Sigma A plus or minus sigma B max. On a cross section, how many normals are there? No, 2 axial and bending. So what the resultant normals in the cross section? Sigma A plus or minus sigma B max. When axial and bendings both are tensile, plus. But axial is the tensile, bendings are compressive, then minus. So these are going to be the different. Try to write down these differences now. Now write down the questions. So today's class, chapter number 5. Chapter number 5 questions. Question number 1. Question number 2. 16. 29. 30. And 20. Nine also. Chapter number 5. These are all the questions. Directly can do it from the class notes now. That is 7 questions are there. You can complete it now. 1, 2, 16, 29, 30, 20 and 9 also. So today's lecture is completed. We'll continue tomorrow. Thank you one and all. So tomorrow we are going to continue. So thanks a lot, Mr. Swaraj Pandey. So I'll upload that more circle conclusions. Okay. So class is completed today. If any queries, you can ask now. But once I am mentioning, when you are solving the problems, axial load, SFD, BMD, TMD, today whatever the sign convention, whatever you have studied, so they are not going to be once again repeated. Please be thorough with the sign conventions and whatever the morning you have done it now. Only one friend is active on the live chat, Mr. Swaraj Pandey. Remaining what not, they are not interactive on the live chat now. What I have to do it, my dear friend, 23 and 27. We already done it. These questions I have already discussed. 23 and 27 already are discussed, my dear friend. Sanjeev Gupta, please refer your notes. 27 is straightforward question now. Already are discussed. If you are unable to answer, mean what now? You are not. Go for unsolved question. Unsolved questions, you can do it now. Sanjeev Gupta, probably you are not. So thank you, Mr. Ankush. Mr. Sanjeev Gupta, please refer your notes. You are asking that question. Question number 27 means that clearly indicates you are not refer the notes. Nobody is going to get a doubt. Question number 27 after attending my lecture now. Probably you are not attended my lecture thoroughly now. You are not gone through that now. So thank you one and all. Please go through the question once again. I have already explained clearly that question also discussed and you are asking the doubt now. Okay. So class is completed. Go through the notes once again. You can able to do it. Please refer the notes thoroughly. You can answer that questions now. Thank you one and all. We'll meet it tomorrow once again.